Welcome to Chemistry Travels. Previously, we've been looking into the several factors that can alter the rate of a reaction. And before we move on to learn about the theories of unimolecular and bimolecular reactions, let's try to solve some of the previous year questions that has appeared for several M.Sc entrances from these topics that we've already dealt with. Okay, and let's start off with some simple questions. So for that, we have our first question here, which has appeared for BHU 2010 paper. And the question says that the rate of the reaction A plus B plus C giving product is given by minus dA by dt equals K times A power 1 by 2 times B power 1 by 3 times C power 1 by 4. And the order of the reaction is, we have to choose one of the options. 4 options are given. Okay, so to find the order, what do we have in the question? We have a rate law or a rate expression or a rate equation for the reaction is given. And from this rate law, how can you calculate the order? From the rate law, what is order? Order is sum of the powers of concentration terms. So these powers, if you just add them up, you would get the order of the reaction, right? So here it is 1 by 2, 1 by 3 and 1 by 4, which is the powers. So adding them up, you would get the answer to be 13 by 12. So this is the order of this reaction. It's a very simple question. Let's move on to another easy question, again from same BHU 2010 paper, and the question says that for a zero order reactions, which of the following is correct? So they've given 4 options, and these options, as you can see, they relate T half-life and the concentration of the reactant or the initial concentration. So how is T half and concentration of the reactant related in case of zero order reactions? And for this, if you remember, when we learned about the general equation for T half for any nth order reaction, we did see that T half can be proportional to 1 by A power n minus 1. We did see that for general equation of T half or half-life for any nth order reaction, T half is proportional to 1 by A power n minus 1. And in our case, for this question, n equal to 0. It's a zero order reaction, n is 0. So just put n value as 0. So my T half turns out to be proportional to 1 by A power 0 minus 1, which is minus 1. A power minus 1. Okay. And now 1 by A power minus 1, I can just reverse it and write it as T half will be proportional to A. Right? So do I have any option that says T half is proportional to A? Yes, my first option says T half is proportional to A. So for zero order, this is the relation that relates half-life and concentration. Clear? Next, we have a very direct question from BHU 2011 paper. So they're asking for a condition for which the reaction rate of an enzymolysis that follows Michaelis-Menten kinetics is half its maximum value. So they want a condition out of the 4, which is the condition that is followed when my reaction rate is equal to half the maximum rate. So if you remember the Michaelis-Menten equation that we learned, and when we learned about the kinetics of enzymatic reactions, we did talk about 3 different cases. One was where my Michaelis constant Km being much larger compared to my substrate concentration, and it would be following a first order kinetics. But if you have my substrate concentration to be larger than my Michaelis constant Km, then it was a zero order reaction. We did have a graph also. And there was a third case when my substrate concentration was equal to the Michaelis constant Km, and that was when my rate of the reaction was half of the maximum rate, right? So from this question, we can easily say that the condition is S equal to Km. That is a condition for which the reaction rate is half of maximum rate. Okay, so option B is the right answer. Clear? Now, if you move to the 4th question, that is from BHU 2012, the half-life of a radium is 1600 years. After how much time will 1 gram radium reduce to 125 mg? So they have given an initial concentration, they have given a final concentration, and they want to know the time that is required for this conversion of radium from the initial to the final concentration. And the extra thing that they have given is the half-life. So for this, you will need 2 equations. One is the half-life equation, another one is the integrated rate law. And which order should we consider? Since they have not mentioned any order as such, or we do not have any equation or anything that specifies which order it is. So we can consider this to be a first order reaction. Okay, so considering this to be a first order reaction, what is the integrated rate law for first order? It is K is 2.303 by T log initial concentration by final concentration, right? So which means we have initial concentration, we have final concentration. We need to calculate T, and now we need the value of K. And to get the value of K, we can get that from half-life, because half-life for first order reaction is T half is given by 0.693 by K. So from that, let's get the value of K first. So T half equal to 0.693 by K implies my K value would be equal to 0.693 by this 1600. And this value will come out to be approximately 4.33 into 10 power minus 4, and this 1600 is in years, so this K value would be in year inverse, right? Okay. Now we have the K value. Now from the integrated rate law for first order, we can say K equal to 2.303 by T log initial concentration, that is A naught by final concentration A. So from this, what can I say? My T value would be equal to 2.303 by this K value, that is 4.33 into 10 power minus 4 log of initial concentration was 1 gram, final concentration was 125 mg. So bringing them to the same unit, I can say this 1 gram is equal to 1000 mg. So I can just write it as 1000 by final concentration is already in mg, that is 125. Clear? Now if you simplify, this 1000 by 125 is 8. 8 is 2 cube. So log of 2 cube you would get, and log of 2 cube can be written as 3 log 2. So from all that, once you simplify, you can get your T value to be approximately equal to 4800 years. Okay. It's not the exact value, but approximately 4800 years would be the value that you get after simplification, which is our option D. So for this question, option D is the right answer. The next two questions are very similar to the previous two questions, and I've just written down their answers here. And we have a BHU 2014 question which says, how many years would be required for the activity of zinc 65 with a T half of 245 days to reduce to 5% of its initial value? So we have some initial amount of zinc that is getting reduced to 5% of its initial value, and they're asking for the time that would be required for this conversion. And for this, a T half is also given. So from half-life, like how we did our previous question, we are going to calculate the rate constant value K. So from T half, you find the value of rate constant K and substitute that K value in your integrated rate law to get the value of time T. Okay. And here our T half is given in days. It's given as 245 days, but the final answer that we need time is in years. So which means you have to convert this T half days, 245 days should be converted to years. So when you convert the 245 days to years, this will approximately come out to be 0.671 years. Okay, T half is so 0.671 years for us. And from the equation of T half, half-life is 0.693 by K. So it means K equal to 0.693 by T half, which is 0.693 by 0.671. Okay, when you do that, you would get the K value to be 1.0327 years inverse. Okay, you got your K value, and now you just have to substitute that in the integrated rate law. So K is 2.303 by T log of initial concentration by final concentration, and for us we have this K value already we calculated, and A naught, let's say we have 100% of the substance, so it would be like 100A. Suppose we have 100A. Now your final concentration is getting reduced to 5%. So you finally have a 5% of the initial one. So 100A would be your initial concentration, and final is just 5%, which is 5A. Okay. So if you do that, your time T will turn out to be 2.303 by this K value, that is 1.0327 log 100A by 5A, and when you solve this, you will get your T value to be 2.9 years, and that is your option D. So option D is the right answer for this question. Let's move on to the next question from BHU 2015. This is also similar to something that you did previously, which is on enzyme catalysis. So here they say that the enzymolysis of a substrate has the Km, Michaelis constant, is given as 0.035 mol liter inverse at 25 degrees Celsius, and the maximum rate of the reaction is given as 1.5 into 10 power 3 mole liter inverse second inverse. And what should be the concentration of the substrate for which the reaction rate would reduce to 0.75 into 10 power minus 3 mole liter inverse second inverse. So even though the question looks quite big, we need not worry. We just have to pick out all the values that are given and write them down separately and check what they are asking for. So when you do that, you will get the answer very easily. So they have given the Km value to be this, they have given the maximum rate also to be this, and they have given a particular rate also. Maximum rate is given and another rate is also given, and they are asking us at this new rate, not the maximum rate, at the rate that is given, what is the value of the substrate concentration that is being asked. So if you look at the rate value, it is 0.75 into 10 power minus 3. Now this is half of this value. It is, you can see that this value that you have 0.75 is half of Vmax, that is half of 1.5 into 10 power minus 3 is 0.75. So the rate that they have given is half of Vmax, and we already saw that the case when rate equal to half Vmax, the condition is that my rate constant will be equal to the substrate concentration. So I can say that my substrate concentration for this particular rate will be same as the Km or the Michaelis constant, and its value is 0.035. So it is 0.035 substrate concentration also, and option C would be my right answer here. Clear? Let's now move on to this BHU 2016 question, where the question says that T half for a second order reaction is 90 minutes and we have to calculate the time that is required for 60% completion of this reaction. So they have given 4 options also. So we just have to, it's similar to the previous questions, but the difference is that this is second order, while previously we were doing it all for first order reactions. Now for second order, T half is already given and T half is in minutes. Our answer is that final time that we need to calculate, the answers are also in minutes. So there is no need for any conversion. So T half can remain as 90 minutes itself. Now we need the initial concentration and the final concentration, which is no value is given. It is only told that the reaction is 60% complete. So if I consider my initial concentration to be some 100 A, so like I had some 100 A, 60% of that is complete. So which means that remaining 40 is my final concentration. So final concentration would be that remaining 40%. So I can just say that this 100 A will be my initial concentration and 40 A would be my final concentrations. So taking it that way, from T half I have to calculate the value of K. So for second order, T half is 1 by K times A naught, and putting the value of T half to be 90 minutes, my K would come out to be 1 by 90 into my initial concentration. I took it as some 100 A. So it was 90 into 100 A. Now from the integrated rate law, Kt is 1 by A minus 1 by A naught for second order, and K value is 1 by 90 into 100 A. So I put that into T is there as such, equals 1 by final concentration is 40 A minus 1 by initial concentration is 100 A or A naught, like you can write whatever. Okay. Since I put it A here, let's keep it A, 40 A and 100 A. Okay, initial final minus initial. So when you do that, and when we solve this equation, you would get the value of T to be 135 minutes, which is option B. So for this question, option B is the right answer. Now moving on to the next question from BHU 2018, we have a chemical reaction is 0 order with K value to be 5 into 10 power minus 8 mol liter inverse second inverse, and how long does it take for the concentration of the reactant to decrease from 4 into 10 power minus 4 mole per liter to 2 into 10 power minus 4 mole per liter. So here also they have given us everything, it's just that we need to know the formula for the integrated rate law for 0 order reactions. K is given, initial concentration is given, final concentration is given. So we just have to know that for 0 order reaction, Kt is given by A naught minus A. So from this you can simply calculate T as 1 by K into A naught minus A, and putting out these values here, K is, so it comes out to be 1 by 5 into 10 power minus 8 times 4 into 10 power minus 4 minus 2 into 10 power minus 4. If you solve this, you will get the t value to be 4 into 10 power 3 seconds, which is my option A. And this is the answer for this question. Okay. Next one is a DU 2017 question. So the rate constant for the substitution reaction increases by a factor of 10.6 when the temperature is increased from 298 Kelvin to 308 Kelvin. Calculate the activation energy for the reaction. So reaction is given and they've told that initially the rate constant was some value K1 at the temperature 298 Kelvin. And they've told that this rate constant increases by a factor of 10.6. So at 308 Kelvin. So at 308 Kelvin, the rate constant is 10.6 times K1. Okay. And they have asked us to calculate the activation energy. So when we learned about the Arrhenius equation, we did see that log of K2 by K1 can be written as EA by 2.303 R into 1 by T1 minus 1 by T2. So if you have K2 here, we have K1 here, we have the two temperatures also T1 and T2. We have the value of gas constant as 8.314. So when you substitute all that, you would get the activation energy to be 181.12 kilojoules per mole. And this is close to which of the following in the options? It is option B. So 181 kilojoules is close to 180, which is my option B. So that's the answer for this question. Okay. The 10th question is DU 2016 question. A radioactive element lost 50% activity in 3 days and 20 hours. The decay constant of the element is dash. So they told that the element has lost 50% activity in some time. So which means that the time that is given is half-life, because if an element, the time it takes for the reactant to reduce to 50% of its initial concentration, that time is called half-life, right? So in this case, 50% activity is lost in 3 days and 20 hours. And now our answer is all in hour inverse. So you have to convert this days also. 3 days and 20 hours should be completely converted to hours, and simply use the half-life formula to calculate the value of decay constant, which is my K value. So T half is given by 0.693 by K. And 3 days and 20 hours will become a total of 92 hours. Okay. Because 3 days is 72 hours plus another 20, so it is 92 hours in total. That is equal to 0.693 by K, and so my decay constant K will become equal to 7.53 into 10 power minus 3 or inverse. And out of all these options, my option A corresponds to this answer. So option A is the right answer. Let's look at the next question from DU 2015. Yes, yeah. So it is for a reaction 2A plus B giving rise to products. Rate law is given by minus dA by dt equal to K into A. At the time T equal to 1 by K, the concentration of reactant is dash, and C naught is given as the initial concentration. So they have given an equation 2A plus B is giving product, and they have told that the rate law is minus dA by dt equal to K times concentration of A. And from the rate law, you can find that order of the reaction is 1. It is a first order reaction because the power of A is 1. So order of this reaction is also 1. It's a first order reaction, and they have told a particular time T equal to 1 by K. So we have to find the final concentration at this time, and initial concentration is C naught. So let's write the integrated rate law for first order reaction. We know that K equal to 2.303 by T log A naught by A, right? So instead of log, since my answer has ln E, I have to write some of the answers like C naught by E, then C naught by E squared. So my options are having E. So I can write that rate law, instead of log, I am taking natural log. Okay, so in that case, my answer, my equation can be written as K T equal to ln of A naught by A, right? This is same as K equal to 2.303 by T log A naught by A. It's the same equation in natural log form. Okay, and now what can we say in this? K into, what is the time here? It is 1 by T, 1 by K. That is equal to ln of, my initial concentration is given as C naught, and it is the final concentration which we don't know. We have to calculate, like that will be some C. K and K will get cancelled off. So finally 1 becomes equal to ln of C naught by C. Now to remove this ln, I can take e power on both sides. So this becomes equal to e power 1 equal to C naught by C. E power ln C naught by C will be C naught by C. So, E becomes equal to C naught by C, or C equal to C naught by E, right? E power 1 is E, so C becomes equal to C naught by E, and this is the answer, which is option A. Next is again a DU 2015 question. The question says that acid hydrolysis of an ester is first order reaction and rate constant is given by K equal to 2.303 by T log V infinity minus V naught by V infinity minus Vt, where V naught, Vt and V infinity are the volumes of NaOH required to neutralize acid present at a given time. If ester is 50% hydrolyzed, then which of the following are correct? So, how would you relate V infinity with Vt and V naught when the ester is 50% hydrolyzed? Okay, so they have given the equation where K equal to 2.303 by T log of initial concentration by final concentration. That is what we have. Or if it's volume, we can say K equal to 2.303 by T log initial volume by final volume. So, what do you understand? This particular thing that you have is my initial volume, yeah, and what you have here, this is my final volume. Okay, let's have that. And what have they told? Ester is 50% hydrolyzed. So what happens when something is 50% hydrolyzed? Now 50% is remaining. So my final volume would be 50% of the initial volume, right? So it's 50 by 100 into initial volume. Okay. Now what is the final volume from this equation? We got the final volume to be V infinity minus Vt. Now that is equal to 50 by 100, that's 1 by 2. I can simplify that as 1 by 2 into, what is my initial volume from this equation? My initial volume was V infinity minus V naught. Okay. Now, I just have to open up the bracket, take this 2 to the other side, open up the bracket and just have V infinity on the left hand side and all other terms on the right hand side. So, how would that come out to be? 2 times V infinity minus Vt becomes equal to V infinity minus V naught. Or after opening the bracket and bringing the other terms to the other side and V infinity on the left side, I would have the final equation to be V infinity equals 2 times Vt minus V naught. So this is the equation that relates my V infinity with Vt and V naught. So this corresponds to my option C that's given here, and that's the answer for this question. The 13th question is from HCU 2019. A complex reaction consists of 3 steps with rate constants K1, K2 and K3, and the corresponding activation energies are E1, E2 and E3. If the overall rate constant of the reaction K equals K1 times K3 by K2, then the overall activation energy is. So, we have 3 different steps for the particular reaction, and K1, K2, K3 and their corresponding rate constants with activation energies E1, E2, E3. And for the overall reaction, they have told that the rate constant can be written as K1 times K3 by K2. Now, how would this E1, E2 and E3 be for the overall reaction? So, for this, we just have to write the Arrhenius equation for each of the steps separately. So, with K1, I can say that K1 equal to A into E power minus E1 by RT, right? We know that. And K2 becomes equal to, this pre-exponential factor A remains the same. So, K2 becomes equal to A into minus E2 by RT. Temperature also remains a constant here. Our gas constant is a constant, A is a constant. It's only K and the activation energy that keeps varying for each steps. Okay. And for the final step, we have K3 equals A into E power minus E3 by RT. Now, what we have to do is, they have told that K equal to K1, K3 by K2. So, let's put all this K1, K2 and K3 here. So, it comes out like K equal to, instead of K1, I am writing as A into E power minus E1 by RT into, now we have K3. So, that is A into E power minus E3 by RT divided by, finally we have K2, which was A into e power minus E2 by RT. Okay, so one of the A would get cancelled off, and finally what I would have is K equal to A into e power minus, I can take this also to the top, and all the E terms, since they have the common base and the powers are different, I can just add the powers or subtract the powers accordingly, right? So when I do that, this becomes minus of E1 minus E2 plus E3 divided by RT is common for all the terms. Okay. So from this, what do you see? This is of the form K equal to A into my e power minus E by RT, where my total E becomes equal to this whole thing. So I can say my E equals E1 minus E2 plus E3. This whole thing is the E, and for the total reaction, my E value, the activation energy, is E1 minus E2 plus E3, which corresponds to the option 1. Here's one more HCU question, 2019 question, and the order of the reaction for which the half-life doubles when the initial concentration of the reactant is doubled is dash. So in this question, it is told that when you double the initial concentration, the half-life is also observed to double. Okay. So we know that T half is proportional to 1 by A power n minus 1, and this is a general equation for half-life for any nth order reaction, and we need to find the value of n such that when my initial concentration increases, T half also equally increases, that is T half is going to be directly proportional to A. So which is that n value? So it is only for a second order reaction when n equal to 2, if you put the value of n as 2, you would get T half proportional to A, T half being directly proportional to A, or when so I can say that when my initial concentration is doubled, my T half equally doubles only in the case of n equal to 2 or the order of the reaction is 2. It's a second order reaction. Okay. And finally, the last question is HCU 2017 question, which says that a reaction follows the general rate law R equal to K times A times B square times C. If the concentration of B is decreased by a factor of 3 and the concentration of C is decreased by a factor of 2, the rate of the reaction will be decreased by a factor of which of these following? Okay, so we are given a rate law which states R is this, and now they are decreasing the concentration of B by 3 times. So this becomes, for the new rate, R dash becomes equal to K times A times B by 3 the whole square times C reduces by 2. So it is C by 2. Now this B by 3 the whole square is B square by 3 square, which is B square by 3 square is 9. So this is B square by 9. And C by 2 is there, and that 9 and 2, 9 into 2 would be 18. So together if I solve this, I would get my R dash, that R dash would be K by 18 into A into B square times C, right. So this top part, K times A times B square times C, that is my R, old R. So the only thing is, the difference is that the 1 by 18 has come. So my new R dash is now reduced by a factor of 80%. 1 by 18, by a factor of 18. So my answer is option C, 18. So it's reduced by a factor of 18. Okay, clear. So these are some of the questions from previous years that has been asked for several M.Sc entrance exams, and maybe in another video we'll look into the questions from our JAM exams for these particular topics, and I hope you understood whatever has been discussed today. Thank you so much.